Hello everyone, this is Sheikh Hania of Sri Venkateswara College of Engineering. Today I am here to present presentation on Laplace transform and its application. So moving forward, we'll first see what are the table of content, what we're going to further learn about the topic. That is about Laplace transform and history, applications of Laplace transform, real life applications and conclusion. Firstly, we'll see what is Laplace transform. So, Laplace transform is an integral transform method which is particularly useful in solving linear ordinary differential equation. It finds very wide applications in various areas of physics, electrical engineering, control engineering, optics, mathematics, and signal processing. The Laplace transform can be integrated as a transformation from the time domain, where inputs and outputs are functions of time, to the frequency domain, where inputs and outputs are functions of complex angular frequency. So, the given below is a formula. So, moving forward, we'll see and know what is the history of Laplace transform, who invented it. The Laplace transform is named after mathematician and astronomer Pierre-Simon Marquis de Laplace, who used a similar transform in his work on probability theory. The side given photo is Marquis de Laplace. Laplace's use of generating functions was similar to what is now known as Z transform. The theory was further developed in 19th and early 20th century by Matthew Sledge, Olivier, and Thomas Bromwich. The current widespread use of transform, mainly in engineering, came about during as soon after the World War II, replacing the earlier operational calculus. The advantages of Laplace transform had been empathized by Gus- Gustav Deutsch, to whom the name Laplace transform is apparently due. So, more ahead, from 1744, Leonhard Euler invested integrals of the form as solutions of differential equations, but did not pursue the matter very far. Joseph Louis was an admirer of Euler, and in his work of integrating probability density functions, invested expressions of the form, which was modern historians have interpreted within modern Laplace transform theory. Also, we have inverse Laplace transform, where we can define it as two integral functions have the same Laplace transform only if they have differ on the set of Lebesgue measures 0. This meant that on the range of the transform there is an inverse transform. In fact, beside integrable function, the Laplace transform is a one-to-one mapping from one function space into another in many other function spaces as well as, although there is usually no easy characterization of the range. Typical function spaces in which this is true include the space of bounded continuous function, the space of 0 to infinity, or more generally, tempered distribution on 0 to infinity. The Laplace transform is also defined and injective for suitable spaces of tempered distribution. In these cases, the image of Laplace transform lives in the space of analytic function in a region of covariance. The inverse Laplace transform is given by the following complex integral, which is known by the various names, where y is a real number so that the counterpart of integration is in the region of coverage of f of x. In most applications, the counter can be closed, allowing the use of residual theorem. An alternative formula for the inverse Laplace theorem is given by post inversion formula. The limit here is integrated in a weak topology. In practice, it is typically more convenient to decompose a Laplace transform into known transform of functions obtained from the table and construct the inverse by inspection. Moving forward, we'll see the application of transform. These are some of the formulas which we learn in the Laplace transform. So, generally, the Laplace transform is used frequently in engineering and physics. The output of linear time invariant system can be calculated by convolving its unit impulse response with the input signals. Performing this calculation in Laplace space turns the convolution into a multiplication, the lateral being easier to solve because of its algebraic form. For the more information, see control theory. So, for more information, we can refer the control theory system. The Laplace transform is invertible on large scale of function given a simple mathematical and functional description of an input or output to a system. The Laplace transform provides an alternative functional description that often simplifies the process of analyzing the behavior of system or in the synthesizing a new system based on a set of specification. The more general now, we're going to see the use of Laplace transform in computer science. A Laplace transform is an integral transform second only to the Fourier transform in its utility in solving physical problems. The Laplace transform is particularly useful in solving linear ordinary differential equations such as those arising in analysis of electrical circuits control system. So these are some of the examples which are using computer science field of Laplace transform, that is control system, probability, integrated circuits, signal processing, data mining. So we'll see what is data mining and machine learning and how Laplace is used in it. Machine learning focuses on prediction based on properties learned from the training data. Data mining, which is analysis step of knowledge discovery in databases, focuses on discovery of unknown properties on data where the Laplace equation is used to determine the prediction and analysis of step of knowledge in database. The second is the signal processing. Laplace transform is heavily used in signal processing. Using Laplace or Fourier transform, we can study a signal in the frequency domain. Laplace transform is subset of the Fourier transform, which is used in processing of data signals during their transmission. For instance, if signal is smooth over time, it means that in the frequency domain, we are very likely to find only small frequencies. Similarly, the concept of filtering signal data is based on the frequency domain interpretation. This, this is catching and cleaning of error generated during a transmission of computer data. The next is control system. The control system manages commands, directs, or regulates the behavior of other devices systems. It can range from a home heating controller using a thermostat controlling a domestic boiler to a large industrial controls. Also, the Laplace transform converts the governing differential equation of system or its components into similar algebraic form, allowing the control engineer to describe the system. In particular, a closed loop system as a chain of connected functional blocks allows called a block system. So next is the integrated circuit. The Laplace information is more useful in integrated circuits. So we'll see how it is. Laplace transformations helps to find out the current and some criteria for analyzing circuits. It is used in building require ICs chips for system. So it plays a vital role in fields of computer science. Next is probability. It is used in probability. It is called movement. It is used in mathematically defined variables in probabilities like variance. Now we have seen most of the uses and applications in computer science. There are many real life applications of Laplace transform, which we can see here, that is analysis of electrical circuits, system modules, digital signal processing, nuclear physics, and process control. So from this all information, we can make out conclusion that the application of Laplace transform is in different engineering field like electronics, mechanical, physics, etc. Beside these, Laplace transform is a very effective tool to simplify very complex problems in the area of stability and control. It goes without saying the Laplace transform in input to tremendous use in engineering field. Thank you for watching the PPD. Hope you like it informative.